Uh, are you able to hear me clearly, Meshak? Am I audible?
Yes, sir.
Okay. We have waited long for everyone. We'll start with the lecture. Are we able to see the screen? Yes.
Yes, sir.
Okay. Did I start with complex number or I have even not started with that? Meshak? Did
Yes,
we
sir.
only complete trigonometry or I started with complex numbers?
Trigonometry, sir.
Huh? Only trigonometry completed. Okay. Okay, I hope you are able to see the screen, right?
Yes,
So
sir.
let's start with the new chapter today. That is complex numbers. Okay, let's start with the chapter as complex numbers. So before starting with what is a complex number, we'll have to understand what is an imaginary number. Okay, which is denoted by I. Actually, it is not I, it is Greek letter which is called as iota, but it exactly looks like I, and that is why we will always say it as I instead of iota. Okay. Uh, so if you
Okay, sir.
remember the 10th standard, you in the quadratic equations you used to write that my root is given by minus b plus minus under root of b square minus 4ac upon 2a. Okay, we used to write roots something like this. Okay, minus b plus minus under root of b square minus 4ac by 2a. And this b square minus 4ac, this term always used to be greater than 0. Okay, it always used to be greater than 0. Why? Because only when it is greater than 0, you get real numbers, something like this. You can get any number in this, okay, square root. And this square root can be positive also, negative also. This is what you have studied in real number. But we haven't studied something like this. We haven't seen under root of minus 1 or under root of minus 5. We haven't seen anything like this. Okay. So how do you represent it? What does the square root of negative numbers imply? So that is why we gave a notation that let under root of minus 1 be I. Okay, let square root of under root of minus 1 be I. This is how we denoted it. Why it is working so slow? So the square root of minus 1 is denoted by I. Okay, the square root of minus 1 is denoted by I. So this under root of minus 5 can be written as under root of minus 1 into root of 5. What's happening? I don't understand. Just wait a minute. Huh? Just wait a minute. Huh?
Okay, sir.
Just wait a minute. This whiteboard is, I just don't know, it is having some issue today. It has just got updated. And after getting updated, it has become completely slow. It didn't even allow me to use the old version. It's working very slow. Yeah.
Hi. Hi. Sir, bonar day. Hello.
Students, are you able to see the screen? Are you able to see the screen?
No, sir.
Are you able to hear me, students? Am I audible?
Yes, sir. Yes, sir.
Students, am I audible?
Yes, sir.
Please reply me in the chat box. Am I audible? Is the screen visible? Please reply me in chat box, am I able to you? Students, am I audible? Students, are you there online?
Yes, sir.
Good afternoon, students.
Good afternoon, ma'am.
No, students?
Okay, okay, sir.
Students, am I audible now?
Yes, sir. Yes, sir.
Okay. Are you able to see the screen? Yes.
No, sir. Yes, sir. Now it's
Okay.
now it's
So I
visible.
was explaining you. Yes. Now you are able to see the screen, right?
Yes.
Yes. So I was explaining you in your 10th standard. When you studied in your 10th standard, we had seen that when b square minus 4ac, okay, you had seen this, that b square minus 4ac, this should be always greater than 0 because this is real numbers. So now here, if it is, what if this number is less than 0, this b square minus 4ac is less than 0. Okay, what if it's less than 0?
Roots are imaginary.
So in that case, we started defining. Yes, what happened? What happened? You're not able to see the screen? What happened, students? This problem with my system today. You can put it in the chat box. So under root of -1 is denoted by I. This is what I said, which is in Greek letter it is called as iota, which is also denoted by I. So we'll say it as I only instead of iota. Okay. So suppose it is something like this, under root of -5. So that can be written as under root of -1 into root 5. So this under root of -1 is nothing but I. So this becomes I and this is root 5. So now whenever you get anything negative in under root, I can represent it something with something like this I, and I get something root 5I. So this I, this is called as imaginary number. Okay, this I is called as imaginary number. This I is called as imaginary number. So now what is a complex number? We started today the chapter called as complex number. So what is the complex number? Generally a complex number is denoted by Z. Okay, it is a combination of real numbers with imaginary numbers. Generally it is denoted as A plus IB, or it is also in many books denoted by X plus IY. It's upon you which notation you want to use. So this A and B, you are writing it as X plus IY. This X and Y, these both are real numbers. If you see here, you have this. This is an imaginary number I. So you just saw that even if it is under root of -5, this is not defined in real numbers. So I wrote it as -1 into under root of 5, which is going to give me under root of -5 only. So this is under root of -5. I was able to write it as I root 5. Now this is the real number and this is the imaginary number. So combination of real number and imaginary number is called as a complex number. So whenever there is real number as well as there is a combination of imaginary number, this combination is called. Okay. So now whenever we study something new, we'll always study the basic of arithmetic or basic of algebra numbers or multiplicative numbers. So same thing will be here also. So how to add it to complex numbers, how to add to subtract numbers, how to subtract two numbers. So that is what we are going to see. So the next we are going to see is called as algebra of complex numbers. Okay. So let me denote one complex number as Z1, as X1 plus I Y1. And let me denote another complex number Z2 as X2 plus I Y2. So if I want to add two numbers, how I will add two numbers and how I'm going to subtract two numbers. So this is only a real number, and here you have this imaginary number over here. So this is called as the real part of a complex number. And this whichever term is there with I, okay, whichever term is there with I is called as imaginary part. So complex number will always have two things. One will be a real part and one will be an imaginary part. Real part, why? Because there is no I. Imaginary part, why? Because there is I. We know, okay, I is called as an imaginary number. So whichever thing is there with I will be called as the imaginary part, and wherever there is no I will be called as a real part. So complex number will always have these two things. One will be a real part and one there will be an imaginary part. The real part will be added and subtracted with the real part, whereas the imaginary part will be added or subtracted with the imaginary part. Okay, so let's see this. So if I want to add two complex numbers, I will add real part with real part, and I will add imaginary part with the imaginary part. So therefore, I can write this as Z1 plus Z2 is equals to X1 plus X2 plus, from here I and I can be taken as common. So from here I'm taking I and I as common. So what will remain inside is Y1 plus Y2. So this is how I can add two complex numbers. So real part got added with the real part, whereas the imaginary part got added with the imaginary part. So suppose instead of this, if I'm writing some numbers, it will become much more clear. So suppose I'm having Z1 as say 3 plus 2y, and I have another complex number Z2 as say 5 my plus 3i. So now we just saw real part will get added with the real part and the imaginary part will get added with the imaginary part, and therefore I will get Z1 plus Z2 is equals to, real part here is 3 and 5. So 3 and 5 will get added, which is going to give me 8, plus imaginary part will get added with the imaginary part. So 3i plus 2i, that is going to give me 5i. So 3i plus 2i, that is going to give me 5i. So this will become 5i. So this is how I can add two complex numbers. Similarly, when you want to subtract two complex numbers, again what you're going to do is, you're going to subtract real part with the real part, and you're going to subtract imaginary part with the imaginary part. So if I'm writing Z1 minus Z2, so I'll subtract 3 minus 5, so that is going to give me minus 2. Similarly, I'm going to subtract 2i minus 3i, so that is going to give me minus I. If I'm doing the opposite, Z2 minus Z1. So I subtract Z1 from Z2. So 5 minus 3, so that is going to give me 2, and 3i minus I, this is the value of Z2 minus Z1. Okay, so I hope you understood it. It's very simple addition. You add real part with the real part, and you will add imaginary part with the imaginary part. Please take the screenshot of this, students. Please take the screenshot of this. Again, I'm trying to start the whiteboard. If it is working, that will be much more fine. I just don't know what is an issue with my laptop today. It's not even getting restarted. That is why you will be facing some issues. I hope everyone has taken the screenshot. Okay. Now let's try to understand how to multiply two complex numbers. Okay, let's see how to multiply two complex numbers. So I have two complex numbers and I have to multiply Z1 into Z2. So Z1 is my X1 plus I Y1 and my Z2 will be X2 plus I Y2. Now multiplication is again simple. The normal bracket multiplication what we do, in the same way we are going to do bracket multiplication over here also. Okay, the way we multiply bracket, so this x1 will get multiplied with x2 and I by 2. Similarly, this I by one will get multiplied with x2 also and I by 2 also. Okay, so let's see what happens after we multiply it. So when I multiply, I'll get x1 into x2 plus I into x1 y2 plus I into x2 into y1 plus this I y1 into this. So I into I, that will give me I square y1 into y2. Now just remember that, if you just remember, we had said that under root of minus 1 is nothing but I. So when I do I square, so this square and square root will get cancelled and I'll get I square is equals to minus 1. Okay, so we had defined that minus 1 is nothing but I. So my I square will give me minus 1. Therefore, this will become x1 into x2 plus, from here I and I can be taken common. So what will remain inside is x1 y2 plus x2 y1. And this I square is minus 1, so I'll write minus 1 into y1 into y2. So now this also became real number. Okay, and this is also real number, and this I is multiplied with this. So this is the entire is the imaginary part. So what I'll do is I'll write real part with the real part and imaginary part with the imaginary part. Therefore, this will become x1 x2 minus y1 y2 plus I into x1 y2 plus x2 y1. So this is how you multiply two complex numbers. Okay, so let us take an example. Instead of this, if I put some numbers, suppose here if I write 5 plus 2i And here, suppose if I write 3 plus say 4i. So now you have the value of x1, x2 and y1, y2. So let us directly put the values over here. So in this case, my x1 is 5 and my x2 is 3. Here, this is my x1, this is my x2, this is my y1, and this is my y2. Okay, so x1 into x2 minus y1 into y2. So y1 is 2 into y2 is 4 plus I into x1 y2. So x1 is 5 and y2 is 4. My x2 is 3 into y1. y1 is 2. So this will give me 5 into 3, that is 15. 15 minus 8, so that is going to give me 7 plus. So when I multiply two complex numbers, which were 5 plus 2i and 3 plus 4i, I got one more complex. Hope you understood how to multiply two complex numbers. Please take the screenshot of this. Let me see if this is working properly. I'm writing and it's still not coming. I cannot use this. I'm writing and it is coming after so many seconds. This is not usable today. Taken the screenshot. Now let's see one more concept before going to division. So now I denoted a complex number z, okay, as x plus iy. Now there is something called as z bar, which is called as conjugate of a complex number. Conjugate of a complex number. So what do I mean by conjugate is simply you have to change sign of imaginary part. Change sign of part. So how to find out conjugate of a complex number? You just have to change the sign of the imaginary part. So if I have this complex number as x plus iy, then its conjugate z bar will be nothing but x minus iy. I only have to change the sign of the imaginary part and not of the real part. Let me give some example. Suppose I have a complex number, say 3 plus 5i. Okay, then its conjugate will be z bar. I just have to change the sign of the imaginary part, so that will be 3 minus 5i. My imaginary part is 5i. Let us see one more example. Suppose I have something like this: 3 plus root 2 plus 6i. So there is a complex number something like this: 3 plus root 2 plus 6i. So which is an imaginary part? Only one which is there with I. So only this is your imaginary part, and this 3 plus root 2 is your real part. So now when you want to take conjugate of this, okay, when you take conjugate of this, you only have to change the sign of the imaginary part. So when I take conjugate of this will remain as it is. This will remain 3 plus root 2. You'll only change the sign of this imaginary part. Here the imaginary part was plus 6. So here my imaginary part will be minus 6i. Okay, I hope you understood the concept of conjugate. Suppose I have one more as complex number say 1. So imaginary part, this is the only imaginary part. This is the real part. So when I want to find out conjugate of this, you only have to multiply, okay, you only have to multiply with its, you only have to change the sign of the imaginary part. So this will remain as it is, 1 plus root 2. Will remain as it is. And this instead of minus I will have to put plus I. Because what is conjugate? Conjugate is nothing but this. Change the sign of imaginary part. You only have to change the sign of imaginary part. Okay, I hope you understood. You only have to change the sign of imaginary part. Okay, please take the screenshot. Please take the screenshot of this. I hope everyone has taken the screenshot of this. Let's move to the next part. So we have seen multiplication of complex numbers also. So just an extension of that. So we just saw so if z is x plus iy, then conjugate of the complex number, that is z bar, is nothing but x minus iy. We just have to change the sign of the imaginary part, right? So what if I multiply this? What will happen if I multiply this? A complex number with its conjugate. So multiplication of complex number with its conjugate will give me z is x plus iy, and my z bar, that is conjugate, is x minus iy. So we know that a plus b into a minus b is a square minus b square. So this can be written as I square y square. Now we know that under root of minus 1 is I, therefore I square is minus 1. So therefore this will become x square. So now I am multiplying a complex number. I am getting x square plus y square. So when you multiply a complex number with its conjugate, you get a purely real number. So if you want to get get purely real number, then what you can do is multiply a complex number with its conjugate. If you are multiplying complex number with its conjugate, you get a purely real number. Let's see what happens if I add a complex number with its conjugate. Z plus Z bar. So that will give me X plus IY plus X minus IY. Will give me 2X. So again I get a purely real number. These are important results which I have to keep in mind. So when I multiply complex numbers, when I multiply a complex number with its conjugate, I get a purely real number. Similarly, when I add, okay, a complex number with its conjugate, again I get a purely real number. Now, if I subtract a complex number from its conjugate, what I'll get? So Z is my X plus IY minus X bar is X minus IY. Now when I open the bracket, this minus minus will become plus and this X will get cancelled and this IY and IY will get added. So I'll get plus 2IY. Now if you see, there is no real part in this case. This real part X and X got cancelled. So you don't have any real part, now you have. When I multiply a complex number, it's a purely real number. And when I subtract a complex number with its conjugate, then I get a purely imaginary number. These are important results. Please take this screenshot. And these results are important. Okay, you will have to remember this result. We'll be using these results during the numericals. Okay. Please take the screenshot of this, everyone. Okay, I hope everyone has understood. Now let's try to understand how to divide two complex numbers. So we saw today how to add two complex numbers, how to subtract two complex numbers, how to multiply two complex numbers. Now we'll be seeing how to divide two complex numbers. So I have something like this. Z1 upon Z2. I want to divide two complex numbers, right? So X1 plus IY1 upon X2 plus IY2. Now, how do we divide two complex numbers is, if you remember in your lower standards, when you used to simplify the surds, okay, that is the irrational numbers, we used to always keep in mind that there should not be any square root in the denominator. If there used to be any square root in the denominator, what we used to do is, we used to rationalize it. So the same thing we are going to do here also. When there is an imaginary number in the denominator, we usually don't like having, okay, an imaginary number are in the denominator. So what we'll do is we'll multiply with its conjugate. Here, there when we used to do rationalize, what we used to do, if it is 1 plus x, we'll multiply it with 1 minus x. Why? Because a plus b into a minus b is a square minus b square. So the same thing is achieved over here by multiplying with its conjugate. So whatever is there in the denominator, okay, multiply with its conjugate. So here in this case, I have x2 plus iy2 in the denominator. So I'm going to multiply with its conjugate. So its conjugate will be x2 minus iy2. So I cannot bring anything from the air, so I will have to multiply and divide with its conjugate. Okay, so I'll get z1 upon z2 is equals to, here I will have to physically multiply it x1 into x2, so that will be x1 x2. This iy1 into iy2, so that will be I square, which we have already seen, so that will be plus y1 into y2 plus I will be common. So here and here when I multiply this and this, when I multiply, I'm going to get this I common. So this will be x2 into y1. And here you have minus signs, minus x1 into iy2. So that will be nothing but x1 into y2. So in the numerator, what I've done is I've physically multiplied the numbers. In the denominator, this is a plus b into a minus b, so that will be a square minus b square. So that will give me x2 square minus I square into y2. And I square is minus 1, so that will become under root of x square plus y square. So then I separate real part with the real part and imaginary part with the imaginary part. So this can be written as x1 x2 plus y1 y2. This was the real part upon this I square is minus 1, minus minus becomes plus. So this will be x2 square plus y2 square plus I into x2 y1 minus x1 y2, the whole upon the same denominator. This I square becomes minus 1, so the same denominator, so that will be x2 square plus y2 square. So this is how you divide two complex numbers. So when you want to divide two complex numbers, what you do is whatever is there in the denominator, you will multiply with its conjugate. Why? Because you don't want any complex number or imaginary number in the denominator. So when you multiply with its conjugate, we have seen when you multiply with its conjugate, you get a real number. So why did you multiply with its conjugate? Because we have seen when I multiply a complex number with its conjugate, I get a purely real number. So to get a purely real number, what we have done is we have multiplied with the conjugate of the denominator, so that I get a purely real number, which is x square plus y square. Okay, so I hope you have understood how to multiply, how to divide two complex numbers. Please take the screenshot of this. Please take the screenshot of this. I hope everyone has taken the screenshot of this. Let's move to next. Okay. So now I'm taking an example. So let my Z1 be say 3 plus 5i and my Z2 be say 2 plus 3i. Now I want to divide both the complex numbers. So let's divide the complex numbers Z1 by Z2. will be equals to 3 plus 5y upon 2 plus 3i. Now, how do you divide? So I said there should not be any complex part or imaginary part. Okay, in the denominator, so I multiply with its conjugate. So conjugate of denominator 2 plus 3i will be nothing but 2 minus 3i. So I'll have to multiply and divide by 2 minus 3i. So I'll get 3 into 2, so that is 6. 5 into 3, that is 15, and I into I, that will be I square, and that I square minus 1 will become plus. So this I'll get 15 plus I into, okay, 5 into 2, so that is going to give me 10 I. I have already taken common, so I'll have to remove. Okay, and this 3 into 3, so that is going to be minus 9i. So here I'm writing minus 9 because I've already taken common upon a plus b into a minus b, that is a square, so that is 2 square, that is 4, minus b square, so I square is going to be minus, so minus minus will become plus. 3 into 3, so 3 square, that is nothing but 9. So I will get z1 upon z2 is equals to 6 plus 15. So that will be how much? 21 upon 9 plus 4, that is 13. Plus I into 10 minus 9 is 1, so only what remains is I upon 4 plus 9, so that is 14. So dividing it with 2 plus 3i, I'm getting answers 21 by 13 plus I by 13. So the real part is written separately and the imaginary part is written separately. Now let's see what happens if I divide a complex number with its conjugate. We've seen what happens when I multiply a complex number with its conjugate, when I add a complex number with its conjugate, when I subtract a complex number with its conjugate. Now let's see what will happen if I multiply a complex number with its conjugate. Okay, everyone please take the screenshot of this. I hope everyone has taken the screenshot of this. So I'm going to the next. Okay. So I'm multiplying a complex number with its conjugate. So let's see what I get. So Z is X plus IY, and its conjugate will be nothing but X minus IY. Now we saw when we divide two complex numbers, the important thing should be their denominator. So I'll multiply with the conjugate of X minus IY. So conjugate of X minus IY will be nothing but X plus IY. So I'll have to multiply and divide with X plus IY. So this will become X plus IY into X plus IY. This will become X plus IY, the whole square. And this A plus B into A minus B, that will be A square minus B square. So we have seen when you multiply, this I square will become minus 1, minus minus will become plus. So let's expand this. So I'll get Z upon Z bar is equal to X plus IY, the whole square. That will be nothing but X square plus 2 I x y plus iy square, so that will become nothing but I square y square upon x square plus nothing but equals to minus 1. So this will become x square minus y square plus 2i xy the whole upon x square plus y square. So real part with the real part and imaginary part with the imaginary part. So this will become x square minus y square upon x square plus y square plus I into 2xy upon x square plus y square. With the conjugate, instead you get a complex number only. We saw that when you are multiplying, when you add complex number with its conjugate, you get again a purely real number. And when you subtract a complex number from its conjugate, you get a purely imaginary number. But when I'm dividing a complex number with its conjugate, I'm not getting any kind of a purely real number or a purely imaginary number. Instead, I get a complex number only. So there's four things you have to remember. Okay, when you multiply a complex number with its conjugate, you get a purely real number. Adding also gives you purely real number. Subtracting gives you, okay, purely imaginary number. Whereas dividing a complex number, okay, with its conjugate doesn't give you a purely real number or a purely imaginary number. Instead, it still gives you a complex number only. I hope you have understood this. Please take the screenshot of this, everyone. Let's move ahead. This is a very important topic. Very important topic of the chapter. Powers of I. Now, why I'm saying like this? Now, see here, I square. We just saw that I square is minus 1. Why? Because under root of minus 1 is I, therefore I square will give you minus 1. Now, suppose if I write I cube. So, this I cube will be nothing but I square into I. Now, I square is nothing but minus 1. So, this will become minus 1 into I, which is going to give me minus I. So, I cube is nothing but minus I. Suppose if I write I raised to 4. So, I raised to 4 can be written as I square into I square. Now, I square is minus 1. So, minus 1 into minus 1. So, that is going to give me minus 1 into minus 1. That is going to give me plus 1. Now, suppose if I write I raised to 5. So this I raised to 5 can be written as I cubed into I square. Now I cubed is nothing but, we just saw it is nothing but minus I, and I square is nothing but minus 1. So minus 1 into minus I, that is going to give me plus I. Now suppose if I'm writing I raised to 6. So I raised to 6 can be written as I raised to 5 into I. Now I raised to 5 is I. So I into I, that is again going to give me minus 1. Now try to see the pattern, okay? Suppose if I'm writing I raised to 7, so which can further be written as I raised to 6 into I. Now I raised to 6 is minus 1 into I, that is going to give me minus I. Suppose if I write I raised to 8, so again it can be written as I raised to 7 into I into I, that is going to give me minus I square. So I square in is nothing but minus 1, and this minus sign, that will give me plus 1. So now if you try to understand the pattern, you will realize that this value only gets repeated. 1 minus 1 minus I, okay, and I. You see, any powers, the same values are going to get repeated. Okay, I, then minus I plus 1 minus 1, this power is only going to get repeated. So I can show it by general terms, something like this. We saw I raised to 4 was 1. So I can write I raised to 4n is equals to 1. Which means I raised to 8, I raised to 12. Go in a table of 4. 4 ones are, 4 twos are, 4 threes are, 4 fours are, and so on. So I raised to 4, I raised to 8, I raised to 12, I raised to 16, I raised to 20, I raised to 24, and so on. Or if I continue in the fourth table, I will get all those powers as always 1. Then I raised to 4n plus 1. So this will give me, if you just see over here, I raised to 5. So I raised to 5 can also be written as I raised to 4 into I. So which can further be written as I raised to 4 plus 1. I raised to 4 plus 1, yes or no? So I raised to 4n plus 1. Okay. So whenever it is that, it is going to give me value as plus I. So I raised to 4n plus 1, that is going to give me value I. Similarly, if I write I raised to 4n plus 2. So let's see over here. You see I raised to 6. This I raised to 6 can also be written as I raised to 4 into I raised to 2, which can further be written as I raised to 4 plus 2. Right? So if I take n is equals to 1, it is 4 into 1 plus 2. So 4n plus 2. And what value we got was minus 1. So I can say whenever it is 4 is 10 minus 2, it is going to be minus 1. And I raised to 4n plus 3. So let's see over here. I raised to 7. So this I raised to 7 can be written as I raised to 4 plus 3. 7 is 4 plus 3, right? So if n is 1, it will be 4 into 1 plus 3, which gave me minus I. So this will be minus I. So this thing you will have to remember it like a formula. Okay, this thing you will have to remember it like a formula. This is called as powers of I. So any power of I you can find out using this formula. So let me give you an example. Suppose I want to find out the value of, okay, I raised to 64. What is the value of I raised to 64? So this I raised to 64 can be written as I raised to 16 into 4. 16 fours are is 64, right? So it became I raised to 4 and I raised to 4 is how much? 1. So I raised to 64 is nothing but it is going to be 1. Suppose I write I raised to 4 into 16, that is 64 plus 1. So I raised to 64, 65 can be written as I raised to 4 n plus 1, and I raised to 4 n plus 1 is how much? I. Therefore, my I raised to 65 is nothing but it is going to be I. Similarly, suppose if I write I raised to 66. So this I raised to 66 can be written as I raised to 4 into 16. So that is going to give me 64 plus 2. So that is going to give me 66. So I raised to 4 and plus 2 is how much? Minus 1. So I raised to 66 is going to give me answer minus 1. I raised to say 67. So I raised to 67 can be written as I raised to 4 into 16, that is 64 plus 3. 67 is going to give me answer as minus 8. 248. 248. This is nothing but can be written as I raised to 4 into 62. 62 4 is 248. So it is I raised to 4, and then whenever it is I raised to 4, it is how much? 1. Therefore, I raised to 248 is nothing but 1. So any power if it is given to you, okay, any power if it is given to you, you can find out. Suppose if I write I raised to 1001. So now 250 into 4 is 1000. So this can be written as I raised to 4 into 250, that is 1000 plus 1. So I raised to 4 and plus 1 is how much? I. Therefore, I raised to 1001 is going to give me I. So see, this is how I can use a result and I can find out the value of I raised to any power. Okay, you can find out I raised to any power. So please take a screenshot of this and I hope you have understood this. Please take the screenshot of this. I hope everyone has understood. Please take the screenshot. I hope everyone has taken the screenshot. Let's move to next. So now we are going to see something called as Argan diagram. So now what is this Argan diagram? So it was a person called as Argan who gave an idea about how we can plot the complex numbers. So now up to date, what you have seen is whenever you draw this, you draw an x-axis and you draw a y-axis. Now this both are real numbers. This is also a real number and this is also a real number. But the question arises as how to plot a complex number. Because here when I take the Cartesian coordinate system, this is also a real number, this is also a real number. Therefore, I will call this as a real plane. Why I call it as a real plane? Why? Because it is having real numbers both. Here also you have real number and here also you have real number. Therefore, I'll call it as a real plane. So what Argan did was he carry forwarded the similar thing and plotted a complex number. So now the complex number we know can be denoted as z as x plus iy. So it had a real part and it had an imaginary part iy, something like this. So what Argan did is on y-axis, on vertical axis, he took the imaginary part and on the horizontal he took the real part. So this is going to give you a complex number because the complex number is nothing but x plus iy. So hence this plane is called as a complex plane. It's nothing complex since we are using an imaginary number over there. So a complex number is a real part as well as an imaginary part. So whenever you try to plot any point over here or draw a graph over here, you'll always write a real part as well as an imaginary part. Hence, this is called as a complex plane. And if I plot any complex number, this will be called as an Argan diagram. So suppose if I'm writing something like this, z is equals to 2 plus 3i. So here I can have this is origin, so this is 0, this is 1, this is 2. Similarly, this is origin, this is 1, this is 2, this is 3, so this 3 and this. So here I am going to get a point. So this is going to be my z. This point is going to be my z. Why? Because it is 2 plus 3i. So this is going to represent 2 and this point is going to represent this point is going to represent 3i plus 3i. So this is how I can represent, okay, this is how I can represent a complex number, okay, on this complex plane, which is also called as Argan diagram. So every complex number will act as a point on the Argan diagram. Okay, I hope you have understood this. Let's move ahead. try to understand something more. So I have this imaginary axis and I have this real axis on Argan diagram. Since this represents real number, this is called as real axis. This is going to represent an imaginary number. This is going to be called as imaginary axis. Okay. I take a complex number which I can write here it as x comma iy. So I'll not write I, I'll just write y because I have already written over there. So if I take this origin and if I connect this origin with z, so I can do a construction, I'll get a triangle, let this angle be theta. So we know this is going to be my x distance. This is going to be my x distance, whereas this is going to be my y distance. By applying trigonometry, I can write sine of theta is equals to, this is going to be the complex, so this is going to be iy, or I can just simply write y, because if I'm talking about a complex plane, I can just simply write it as y. Okay, opposite upon, let me represent this as r. Similarly, I will get cos theta is equals to adjacent, that is x, upon hypotenuse, that is r. So now if I square and add, what I'll get is sine square theta plus cos square theta is equals to y square by r square plus x square by r square, which can further be written as denominator is same, so I can write it as x square plus y square upon r square. This sine square theta plus cos square theta is 1, therefore I'll get 1 is equals to x square plus y square upon r square. So this r gets multiplied with 1, so r square into 1, so that is going to give me r square so I'll get r square is equals to x square plus y square which can further be written as r is equals to under root of x square plus y square. So this is what I've, this is called as modulus of a complex number. Then what I'll get So I'll get something like this. Sine theta by cos theta is equals to, the value of sine theta was y by r, and the value of cos theta was x by r. R gets cancelled, and sine theta by cos theta is nothing but tan theta. So I'll get tan theta is equals to y upon x. So this tan theta goes over there. So this same thing can be written as theta is equals to tan inverse of y by x. This is called as argument or amplitude of a complex number. Argument or it is also called as amplitude of a complex number. Of complex number, so it can also be denoted as arg of z. It means argument of a complex number. It means this. So argument of a complex number can be denoted by something like this, arg of z. Similarly, modulus of a complex number, which is r, is nothing but equals to r. Okay, so please take this screenshot of this. I hope you understood what. Come to the next type of next representation of complex number. So initially we saw today as one representation of complex number as x plus iy. Now we are going to see further two more representation of complex numbers. One is called as the polar form and the other is called as the exponential form, which will be using this, and that is why I taught you what is modulus and what is argument. I hope everyone has taken the screenshot of this. Take the screenshot of this also. Please take the screenshot of this also. Okay, I hope everyone has taken screenshot of this. So we move to the next form, which we call it as polar form. Polar form of a complex number. So how do you write polar form? So what we have seen early in the lecture was we call it as Cartesian form of complex number. Whenever things are written in terms of x and y, okay, it is called as Cartesian. So here initially we wrote it as x plus iy, so that is called as Cartesian form. Now this is polar form. So this is something like this. R into cos theta plus I sin theta. So if I write a complex number in this form, this is called as polar form of a complex number. So where R is modulus and theta is the argument. Okay, R is the modulus of a complex number and theta is the argument of the complex number. So if you know theta and if you know argument and modulus of a complex number, you can also write something like this. in the form of r into cos theta plus I sin theta. We have one more form which is called as exponential form. So exponential form, we write complex number as z is equals to r into e raised to I theta. So if you write complex number something like this, r into e raised to I theta, it is called as exponential form. Why? Because e raised to x, this is called as exponential function. So whenever you write something e raised to something, it will be always called as exponential. So what is this e raised to I theta? This e raised to I theta is nothing but this e raised to I theta can also be written as cos theta plus I sin theta. So let's see how to convert one form of complex number into another form. So suppose I have something like this, z is equals to root 3 plus I. So I have a complex number as z is equals to root 3 plus I. I want to convert it into polar form. Now for polar form, what you require is r and theta. So how do you get r and theta? When you compare it with x plus iy. So you can write nothing but your x is equals to, if you compare, you get x is equals to root 3 and you will get y is equals to 1 when you compare it. So then you can directly put it into the formula. So we have just derived that r is nothing but equals to, that is modulus is nothing but equals to x square plus y square. So from here I'll get r is equals to under root of root 3 square, that will be 3, and 1 square, that will be 1. So square root of 4, that is 2. So I get modulus is 2. Argument. So how do you find out argument? So this argument of complex number is nothing but theta is equals to tan inverse of y by x. So this will be nothing but upon x, that is root 3. Okay, so by 2. So 2 gets cancelled, you get 1 by root 3. So for tan 30, you get 1 by root 3. So tan inverse of 1 by root 3 will be nothing but 30 degree. So now in the polar form, I can write this complex number as r into cos theta plus I sin theta. So r, that is 2 in this case, into cos theta. So theta is 30 degrees. So you can write it as cos of 30 degree plus I sine of 30 degree. So this is in the polar form. So I was having a complex number in the Cartesian form and successfully I was able to convert it into polar form. The screenshot of this. So I had Cartesian form, and from Cartesian form I converted into polar form. I can do the opposite also. Suppose if I'm given with modulus and argument of complex number and I want to write it in the Cartesian form, I can do that also. I hope everyone is taking the screenshot. So let's see that. Suppose we have been given as modulus is say equal to 2 and theta is say equal to 60 degree. And I want to convert it into Cartesian form. So very first thing what I'll do is I'll write it in polar form and then I'll just simplify it. So I can write it as r into cos theta plus I sin theta. So 2 into cos theta, that is 60 degree, plus I sin theta, that is sine of 60 degree. So that will give me 2 into cos of 60 degrees is how much? 1 by 2. And sine of 60 degrees is how much? Root 3 by 2. So now this 2 can be taken common and it can be cancelled with this. 2 will get cancelled, so I'll get 1 plus I root 3. So I was knowing in the polar form and I have successfully converted into Cartesian form, that is x plus I by form, that is 1 plus I root 3. So this is how you can convert from one form of the complex number to other form of the complex number. Okay, from Cartesian to polar, from polar to Cartesian. Okay, an exponential, nothing difficult, it's easy. So in exponential, how do you write r and raised to, so r value is already there, that is 2 into e raised to I theta, so I into theta, theta is how much? 60 degree. But when you write in the exponential form, you don't write in degrees, you write in radians. So you write it as 2 into 60 degrees, how much? Pi by 3, right? So I can write e raised to I pi by 3. So when I write in exponential form, okay, we don't write in degrees, we write in radians. 60 degree in radians can be written as pi by 3. So this is in the exponential form. So this is how I can convert or I can write from one form of complex number into another form of complex number. So everyone please take the screenshot of this. I hope everyone has taken the screenshot. Today we have faced a lot of technical glitch. Okay. So today's lecture is over here. We'll meet in the next week. I'll be coming to Nagarcoil. So we'll meet physically next week. Okay. Have a nice day ahead.